Okay, good morning. Today we're going to go through chapter 17. The first concept we're going to go through chapter 17 is actually to introduce the concept of oxidation numbers. Okay, so this actually probably actually one of the most important things that you need to actually get really familiar with um, for this chapter. Okay, so here I summarize a few rules that will help you to understand and estimate the oxidation numbers of a specific atom. Okay, so the rule number one is that if you have only a single atom species, then its default oxidation number will simply equals to 0. Okay, for example, O2, H2, and N2. All these species are single atom species. Therefore, for all these three, the oxidation number will simply equals to 0. Okay. Second things, if you have a monoatomic ion, okay, so here specifically is actually for ionic species, okay, then its oxidation number will be the same as its ionic charges. Okay, for example, if today you have Na plus, okay, so this is actually monoatomic ion, right? Therefore, the oxidation number of sodium will simply equals to 1. Rule number 3, if today you have a compound, okay, meaning a chemical species, they contain multiple atoms, okay, then these are the rules that you need to actually get familiar with. The first thing is that if you see the oxygens inside your compound, its oxidation number is typically -2. The only exceptions is that you have a peroxide. Under this specific case, then the oxidation number of your oxygen will be -1. Similarly, if you have an atom that is H, okay, then inside your compound, the H will actually carry +1 oxidative number. The only exception is if you have a compound that contain your H together with your 1A group members, then you have the hydride. And under that case, you need to count the oxidation number of the H as -1. Next thing is inside your compound, if you have a 1A group, which is this column, then all the things will carry +1 charges. And if you have a 2A, then it's going to carry +2. Similarly, if you have 7A, then it carries -1. 6A carries -2. Okay, so let me highlight these columns so you can really know where to look for them when you look at your periodic tables. Okay, so these are the simple rules that you need to be very familiar with. Okay. The very last one is that the sum of the oxidation number of a compound, it must either be 0 for the electrical neutral compound, or it has to be equal to the charge of the ions. For examples, if today you have a compound, let's say MnO4, okay, so this species by itself is neutral. Therefore, all the oxidation sum of all the atoms need to be equals to 0. Okay, so in this case, we know if you have oxygen inside a compound, you're going to assign -2 charges for it because you have 4 of them. Therefore, you multiply by 4. And then since this is a neutral compound, then you know the oxidation number of your manganese, okay, Once you add up with these oxidation numbers, it has to be equal to 0. Therefore, you know the oxidation number of your manganese for this case will be positive 8. Okay. Typically, your MnO4 will exist. If today your MnO4 exists in the -1 charge, then the oxidation number of your manganese O4 minus, it should be -1, right? So your oxygen still carries -2. You have 4 of them. That means your manganese will become positive 7. Okay, so this is just a simple example that if your compound carries a charge, then all the oxidation number sum of all the atoms will actually equal to the charge. If there's actually no specified charge on the top right corner, then the oxidative number sum of all atoms will equal to 0. Okay, so this is actually the first examples that to show you how to calculate the oxidation number of different atoms. Okay. Once we know how to calculate the oxidation number of different atoms, then based on its oxidation number changes from the reactant to the product side, we can actually start to understand the redox reactions. So redox reaction is reactions they are going to have both oxidation reaction and reduction reaction happen simultaneously. Okay. To really figure out which ones undergo oxidation and which one undergoes the reduction reactions, from the YouTube videos that you should have watched, okay, you should know that we are going to use two terms. One is called the LoRa, the other one called the GROC to specify all these changes. The LoRa is short of lost electron, oxidation. By itself, it can serve as a reductant, and then this reaction will always happen at the anode, okay, where we always have negative sign, okay. Similarly, for the G-rock is actually the species who gain electron, it undergo the reduction. Itself can serve as an oxidant, and this reaction will happen in the cathode. Okay, so LoRa and G-rock, are the two most important process that you need to actually be able to identify for this chapter. One of the most important thing of this chapter is to ask you to balancing the redox reaction. Okay, so here I summarize the 4 steps to actually achieve the balanced redox reaction. Okay, the first step is that you need to actually identify the 2 half reactions. Namely, you need to actually identify who is actually your LoRa, who is actually your GROC. Okay. Once you have the LoRa and GROC written out, the next thing is actually you want to actually balance these 2 half reactions by starting from balance the atoms. Okay. When you balance the atoms, the question will actually specify what kind of condition you have. Since this is actually a redox reaction, meaning actually your charged species need to be actually freely diffused inside your solution. Therefore, your solution is typically either acidic or basic. Okay, so this actually brings a very important point that to balance the atoms for the acidic solutions, we are going to use H plus to account for the missing H, H2O to account for the missing oxygen. Okay, if you have acidic solution. However, if you have a basic solution, then you will use H2O to account for the missing H, and you're going to use 2OH minus to account for the missing oxygen. Okay. So these are the very simple rule, but important rules that we should actually memorize. Okay. And then once we actually balance all the atoms, then we'll need to actually try to balance all the charges of these two half reaction by using electrons. And the very last step is that we want to actually make sure the two half reactions have the same electron gains and loss. Once we can actually achieve that, then the very last step is actually just add up these two half reactions so that we can get the balanced redox reaction. Okay, so these are the four major steps. We are going to practice a lot for today's lectures. So we're going to practice in our homework, in our hangout, we have 1, 2, 6 this kind of questions. We are going to go through all of them one by one so you can actually get familiar with this process. All right, so let's look at our question number 1. Okay. So the question says, balance the following reactions in the basic solution using the lowest possible integers and giving the coefficient of hydroxide ions. Okay, so you know you're actually on the basic solution, right? So if you want to compensate the missing H, you are going to use H2O. If you want to compensate the missing O, you are going to use 2OH minus. Okay, so that's actually the first things that we should actually know. Second, the question is actually asking what is the coefficient in front of your hydroxide ion. Therefore, we want to actually identify the coefficient in front of your OH minus. Okay. But before we can do all those things, we need to actually look at our equations and identify who is actually our LoRa, who is actually our G-Rock. Okay, so in order to do that, we need to actually first identify the oxidation number of each individual atom. Okay, so the first molecules that we see here is actually MnO4 minus. Okay, therefore you know the net charges of this species is -1. Okay, and then we know oxygen typically you have -2. Now we have 4 of them. Okay, so this actually give you -8. Since the total charge is actually -1, what it tells us is that for your manganese here, it will be +7. Okay, because +7 minus 8 will give you -1. Okay. Move on to the second molecule. We can see that the negative charge is actually 2 minus. Okay. We still have 4 oxygens. The oxidation number of oxygens is -2. You have 4 of them, therefore you have -8 in total. Since the total net charge is -2, therefore we know the total positive charge of your C2 is +6. And then since we have 2 of them, therefore you actually divide it by 2 so that we know the oxidation number of a single carbon will be simply +3. Okay. So next molecule, MMO2. So this is actually a neutral species. Okay, you have 2 oxygens. Each oxygen contribute to -2 charges. You have 2 of them. So this actually give you -4. Since the molecule by itself is actually neutral, that means your manganese in here has to be +4. Okay, very last molecules. So CO3 2 minus, you have a total oxidation number of -2. You have 3 oxygens, so this is actually -6. In order to give you a net charge of -2, here you know your C will need to be +4. Okay, so let me highlight the oxidation numbers for all these species. Okay, so if we focus on the manganese, its oxidation number goes from +7 to +4, meaning it's actually gaining electrons, right? It gains 3 electrons. Therefore, you know, gaining electrons, so your manganese is actually your G rock, right? So you're going to have your LoRa, you're going to have your G rock. Okay, so here you know you're going to write MnO4 minus, then eventually becoming your MnO2. That's your G rock, right? Your LoRa apparently will be your C2O4 2 minus, and then becoming CO3 2 minus. Okay, so by writing out your LoRa and G rock, then we finish the step number 1. Then we can actually move to the step number 2. We need to actually balance all the atoms. Okay, and then we are going to use H2O to compensate your H, using 2OH minus to compensate the mixing oxygen. Okay, but before we do that, you want to actually make sure that this non-hydrogen or non-oxygen atoms need to be actually balanced first. Okay, so we need to do that. So in order to do that, we actually multiply 2 to actually get it done first. Okay, so by doing that, then the carbon on both sides are balanced. Okay, then we start to actually compare the number of oxygens on both sides. Here, you have 4 oxygens. And then in your product side, you actually have 6. Therefore, on the product side, you actually have on the product side, you actually have 2 more oxygen. Okay, so since you have 2 more oxygen on the product side, that means actually to actually add in the oxygen in your reactant side. Okay, so 1 extra oxygens on the product side will actually, in order to compensate, you can actually add in 2 equivalent of OH minus to do that. Okay, so we're going to add in 2 equivalent of, you have 2 OH minus on your reactant side. Okay, so this will simply becoming 4 OH minus. Okay, so once you do that, you'll realize that you actually introduce 4 extra H on the left-hand side. Therefore, you need to actually compensate that by using the H2O. Okay, so since right now you have 4H extra on the reactant side, then you can actually add in 2 H2O to balance it out. Okay, so in the basic solution, this is actually typically what you will need to do. First, you need to actually balance your hydroxide or oxygen. Then you come back to balance it again using your H2O. Okay, and after you do this, then you can check. On the left-hand side, you're going to have 4 oxygens plus 4 oxygens, therefore totally 8 oxygens on the left. On the right-hand side, you have 6 oxygens plus 2 oxygens. Therefore, you also have 8 oxygens on the product side. Then we actually check the hydrogen. Okay, so you have 4 hydrogens here, and you also have 4 hydrogens here. Okay, so up to this point, you can see all your atom has been balanced. Okay. Similarly, we're going to apply the same concept for your G rock. Okay, so the manganese has already been balanced. Okay, then you compare the oxygen. So on the left-hand side, you have 4 oxygen. On the right-hand side, you have 2. So you actually have 2 extra oxygen on the left. Therefore, we know we need to add in 4 OH minus. Okay, so 1 oxygen is going to need 2 OH minus to balance it. Okay. Once you do that, then you can see you have 4 extra hydrogens on your product side. Therefore, we need to add in 2 H2O to balance out your proton. Okay. So by doing that, you can see that right now you have 4 oxygen plus 2, so you have 6 oxygen on the left. So on your product side, you have 2 plus 4 is also 6. Okay. Checking out the H, you have 4 here, and you also have 4 here. Okay, so by doing this, then we actually balance out your G-rock as well. Okay, after we balance out the atom in your both LoRa and G-rock, the next step is actually to balance out the net charges on both sides of your LoRa and G-rock. Okay, so with that being said, okay, let's focus on the charges now. Okay, so this contribute to -2 charges. This contribute to -4 charges. Therefore, on the left-hand side, you have totally -6. Okay. On your product side, here contributes -4. Here, this is neutral, so this is actually 0. So, therefore, we know on the left-hand side of your LoRa, you have -6. On the right-hand side, you only have -4. Therefore, what we do is actually we're going to add in 2 electrons. Okay, so we can actually balance out the charges. Okay. After that, we are going to repeat the same process for our G-rock. Okay, so for our G-rock, the first ion actually give you -1. Second one is actually neutral. On the right-hand side, you can see this one is actually neutral. This one will give you -4. So to balance the charge, we need to add in 3 electrons on the left-hand side so that it will be balanced. Okay, so once we do that, then we finish the step number 3. The very last step that we will need to do is actually we want to actually start to compare the electrons that got produced and consumed. Are they the same? If they are not, then we need to actually make it the same before we can actually adding up. Okay, so apparently in this case, they are actually not the same because in your LoRa, you actually contribute only 2 electrons, but in your G-rock, you actually take 3 electrons. Okay, so to make it the same, we need to actually multiply 2, multiply 3 for your LoRa, and then multiply 2 for your G-rock. Okay, so once we do that, what we're going to get is 3 C2O4 2 minus plus 12 OH minus is going to become 6 CO3 2 minus plus 6 H2O and then plus 6 electrons for your LoRa. Your G-rock will become 6 electrons plus 2 MnO4 minus plus 4 H2O that gives 2 MnO2 plus 8 OH minus. Okay, so after we do this, then we can actually check these 2 equations. Okay, now you have the same amount of electrons. Okay, then what we do is actually we're just adding up. Okay, so once we're adding up, this will cancel out. Okay, so the AOH minus will actually cancel out with this, so you only have 4OH minus remains. Okay, and then you have 4H2O, so that cancel out, so you only have 2H2O remains. Okay, so after you do all these things, then you're going to have the final equation that starts with 3C2O4, 2 minus plus 4 OH minus. So this actually from here plus 2 MnO4 minus, which is from here. So that's actually all the things you're going to have for your reactant. For your product, what you're going to have will be 6 CO3 2 minus plus 2 H2O. And then for your G-Rock, you have plus 2 MmO2. Okay. So let me reorganize this one. So the final equation you're going to get will be 3C2O4 2 minus plus 4OH minus plus 2 MnO4 minus is going to give you 6 CO3 2 minus plus 2 MnO2 plus 2 H2O. Okay, so once you have done all these things, then it is asking you what is the coefficient in front of your hydroxide ion. Okay, so what you will need to do is actually first to identify your hydroxide ion. And therefore, this will be the coefficient that you should actually input for these specific questions. Okay, so this is actually how you balance the specific equations. All right. Okay, so let's move on to the second questions. Oops. Okay, so the second question says, balance the following equation in the acidic solution. Using the lowest possible integer and give the coefficients of H plus. So you need to actually find out the coefficient in front of H plus, right? So first thing first, since you have acidic solutions, right? Therefore, you know, if you want to actually compensate the missing H, you use H plus. If you want to actually compensate the missing O, you use H2O. Okay, so this is actually the first things that we need to know. Okay, then we can actually look into this equation and figure out who is actually our LoRa, who is actually our G-Rock. Okay, so CO2. Okay, so CO2 is a monoatomic molecule, right? And by itself is actually neutral. So based on our rules that we know the oxidation number of your Cl will equals to 0. Okay. H2S. Okay, so the H is typically always plus 1. You have 2 of them. So this gives you plus 2. Since the overall molecule is actually neutral, and the way I know is actually because it doesn't carry any charges, so it's actually neutral. Okay, therefore you know your sulfur should actually have -2 charges. Okay. After the reactions, you form a species S, right? So this is actually a single atom species and it's actually neutral. Therefore, its oxidation number will become 0. And then Cl minus, again, single atom species. Since this one carries -1 charge, therefore you know the oxidation number of your Cl will be -1. Okay. Then we can start to compare the oxidation number changes of your different atoms. Okay, so for CO to here, okay, from reactant to product, its oxidation number goes from 0 to -1. Therefore, we know that it's actually our G rock, right? And then for your sulfur, it goes from -2 to 0. So give out 2 electrons. Therefore, this is actually your LoRa. Okay, so we can actually write it down. Your LoRa will be H2S becoming S. Your G rock will start from Cl2 and become Cl minus. All right. That's our step number 1. Step number 2, balance the atom, right? So here is actually your target atom. Your target atom has been balanced already. You have 1 on each side. The next thing is actually you want to actually balance the H or oxygen, right? So here you have 2 extra H on your reactant side. Therefore, you know on the product side, you actually add in 2 H plus. Okay, so we add in 2 H plus is simply because you have acidic solution. Therefore, you compensate that H using the H plus, and you are actually short of 2. Therefore, you put 2 H plus here. Okay, and once you do that, it's done, right? Because right now you have both the same number of H and the S on both sides. Therefore, you're done with that correction. Okay. Moving to your G rock. So here you only have your target atom. Okay, so you simply multiply by 2 on the product side. Therefore, you actually balance all your atoms. Okay. Once you balance your atom, the next step is actually trying to balance the charges. Okay, so here, this is neutral, right? So you don't have any charges on the left-hand side. On the right-hand side, this is actually neutral. This is actually 2 plus. Okay, so to balance your charge, we know we need to actually add in. We need to add in 2 electrons so that the charges on both your reactant and product side will be balanced. Okay, similarly for your G rock, this is actually 0, this is actually -2. Therefore, you need to add in 2 electrons to balance the charge. Okay, so after doing that, we balance all the charges, then we can actually move to the next step. Okay, so we want to check whether the electron that's given out from your LoRa the same as the electron that's actually uptake by your G rock. Okay, so in this specific case, they are actually exactly the same. So the other thing you need to do is actually you're just adding up. Okay, therefore on the reactant side, you have H2S plus Cl2 plus 2 electrons. On the right hand side, you have S plus 2H plus 2 electrons plus 2 Cl minus. Okay, and then 2 electrons will cancel out. So in the end, what you have is H2S plus Cl2 that give you S plus 2H plus 2 Cl minus. And the specific questions is asking you for the coefficient in front of your H plus. Therefore, we know the answer will simply equals to 2. All right, so it's basically the same process that we have went through in the question number 1. The only difference is that in question number 1, we actually conduct all the things in a basic solution. Okay, therefore we use H2O to compensate the missing we use the H2O to compensate the missing H, and then we use 2 OH minus for the missing oxygen. Okay, but in the acidic solution, we simply use H plus to compensate for your H and H2O for your oxygen. Okay, so that's actually how you solve the question number 2. Okay. Moving on to the question number 3. Okay, so question number 3 is actually somewhat interesting questions. Okay, so let's read the question first. Okay, balancing the following equations in basic solution. Okay, so in basic solution, we know if you want to compensate for your H, you're going to use H2O. Compensate for your oxygen, use 2OH minus. Okay, and they want to know what is the coefficient in front of your OH minus. Okay, so the same thing. Okay, you need to actually first identify who is actually your low log, who is actually G log. Okay, so if you look at this equation, okay, you can actually first identify the oxidation numbers, right? So single atom species in the neutral form, therefore the oxidation number will be 0. Okay. Here you see the things is CM minus. Okay, and then you also see CM minus actually show up here. Okay, so this is something that you want to be careful when you're handling a question like this. Okay, typically we call this species as a complex anion. Okay, and then the commonly seen complex anions including Cn minus, NO3 minus, SO4 2 minus, PO4 3 minus. Okay, so every time you see these complex anions, okay, so you don't actually worry about the redox reaction of all these species. Okay, because typically these things doesn't undergo a redox reaction by itself. Is actually a very stable species. Okay, when you encounter a species like this, okay, you can simply put them as a X. Okay, and then that thing doesn't really change. That thing is not going to play any roles in your redox reaction. Okay, so trying to you don't actually really worry about it. Okay, that is not your focus. Okay, so here we will just use X to represent this species for now. Okay, then move on to the next molecules. O2. Okay, single atom species is neutral. Therefore, the oxidation number of your O will simply equals to 0. Okay. Then we move on to the next molecules. Okay, so you have a CN2 minus. Okay, so each CN we know it carries -1 charges, and you have 2 of them. Okay, and then the overall molecule carries -1. That means actually your Ag here will carries +1 charge. Okay, and then move on to here. We know your H is +1. Your O is -2. Okay, -2 with +1 is why you have a negative charge of -1. Okay, so once you have all the things written out, then you can start to analyze the change of your oxidation numbers. Okay, so here you go from 0 to +1. Therefore, you know for your Ag is undergo a LoRa, right? Here, your oxygen go from 0 to -2. Therefore, this will be your G-rock. Okay. So with that being said, we can write out your LoRa will be Ag becoming AgCN2 minus. Your G-rock will be O2 becoming OH minus. Okay, so this will actually conclude the first step number 1. Okay. Step number 2 is actually to balance the atoms, right? So if you look at your target atom, you have one Ag here, one Ag there. So for the Ag, it's already balanced. Okay, then you start to looking for the remaining part. You have Cn2 minus, right? So since you don't have Cn on the left-hand side, therefore this actually time you actually add in 2 Cm minus on your left-hand side. Okay, and after that, you are done, right? Because you have the same amount of Ag, the same amount of Cm minus. Okay, then you can just move on to your G-rock. Okay, on the left-hand side, you have your O2. On the right-hand side, you have your OH minus. Okay, and then here you are in the basic solution. Okay, so this is actually a very interesting case that you want to be really careful. Okay, so we know to balance the oxygens, we are going in the basic solution, we are going to use, okay, if you're missing one oxygen, then you're going to have 2 OH minus adding up. Okay, then if you look at here, okay, here you have O2, right? And then on the right hand side, you have OH minus. Okay, every time you encounter this interesting situation, this is actually what you need to do. Okay, you have O2 on your left hand side. Therefore, on the product side, you're going to expect to have 4 OH minus, right? So here, you already have 1 OH minus, right? So what you do is actually you just simply multiply 4 right here, okay? So once you do that, you're going to introduce 4 extra H on the product side. Therefore, to compensate that, I'm going to actually add in 2 H2O to compensate for the H. Okay, and after you do that, you realize that, okay, your G-rock is also balanced. Okay, then we can just move on to the step number 3. Okay, number 3 is actually to balance the charge of your LoRa and G-rock individually, right? So here, the Ag doesn't carry any charges. 2 Cm minus give you -2. Okay, and then you have one molecule AgCN2 carries simply -1 charges. Okay, so you can see that your product side is short of 1 electrons, right? So we add in 1 electrons for your LoRa, right? Okay, and then if you look at your G-rock, okay, so here you can see you have O2 is actually doesn't carry any charges. H2O doesn't carry any charges. 4OH minus actually carries -4 charges. Okay, so to balance the charge of your G-rock, then we know we need to add in 4 electrons on the reactant side. Okay, so once you have the things, then we can see, okay, so here you actually give out one electrons, and then here you uptake 4 electrons. Therefore, it is not balanced. So you need to actually balance it first. Okay, so what you're going to do is actually you're going to multiply your LoRa by 4 and then add up to your G-Rock. Okay, so once you do this, the net result will look like this. Okay, I'm going to write out the result directly. Okay, so you're going to have 4 Ag plus 8 Cm minus plus, so this actually from your LoRa. Okay, from your G-Rock, you're going to have 4 electrons plus O2 plus 2H2O. So that's actually all the things that you have uh, on the reactant side. On the product side, you're going to have 4 AgCN2 minus plus 4 electrons. Okay, and then for your G-Rock, you have 4 OH minus. Okay, so once you write these things out, then you can see that 4 electrons, 4 electrons will cancel out. Okay, so all you have remained will be 4 Ag plus 8 Cn minus plus O2 plus 2H2O. That's going to give you 4 AgCN2 minus plus 4 OH minus. Okay, so this will be the balanced redox reaction we're actually looking for. And then here we're actually looking for the coefficients in front of your OH minus. Therefore, the answer will simply equals to 4. Okay. So two interesting things in this question is that we start to see the so-called the complex anions, right? So what we do is actually we just treat them as okay, commonly used species. Okay, we can actually consider it actually just as a species there we always use, and it doesn't really change and involve in your redox reaction, but we just use it to actually balance the atoms. Okay. Second is that if you encounter this situation where your OH minus is actually part of your uh, species inside your reaction in the basic solution. Okay, so what you do is actually you first look at, in this case, okay, in the reactant side, you have O2. Then you first to think about how many OH minus that you will need to have. Okay, so since you have 2 O2, therefore you're going to have 4 OH minus. Okay, so since originally you already have 1, then you actually add in only 3 OH minus in your on your product side. Okay, so those are the little things that you want to pay attention to for this specific question. All right, so this is actually how you solve question number 3. Okay, then next questions. Okay, balance the following equations in acidic solution. Okay, so since it's actually acidic solution, therefore we know if you are missing H, you use H plus. If you're missing O, you use H2O. Okay. Using the lowest possible integer and give the coefficient in front of H2O. So a coefficient in front of your H2O is actually the things we're actually looking for. All right, so let's look at this. First thing first, identify the oxidation numbers. Single atom in its neutral form, oxidation number will equal to 0. Okay, so here is another example of the complex ion, right? So NO3, NO3. So those are the species that you know you probably won't try to do too much with it, okay? So H is +1. Okay, and then you look at this NO3. Okay, so this is actually a very interesting case because on your right-hand side, you only have two species. One is actually a copper, one is actually your HNO3. Okay, that means actually to have a redox reaction, you must have one thing called oxidation, one thing called reduction. Okay, since you only have two, that means actually this NO3, even though it's actually a complex anions, okay, you will actually still need to analyze its oxidation number individually. Okay, so you have three oxygens, so it's -2 multiplied by 3, which give you -6. Okay, the overall molecule is neutral, right? Therefore, you know your N will equals to your N is going to have an oxidation number of +5. Okay, go back to here. Okay, your NO3 is carry -1 charges. Okay, you have two of them, therefore you have -2. Okay, the overall molecule of your CuNO3 is 0, right? It's neutral. Therefore, you know your copper is going to carry is +2. Okay. NO2. Okay, so overall a neutral molecules, you have two oxygens. That's -2 times 2. Therefore, this is actually -4. Therefore, your N is +4. Okay, and then H2O will be O is -2. Your H will be +1. Okay. So if you look at this, the easiest one to see the undergo oxidation reaction will be your Cu, right? So it go from 0 to +2. Therefore, this is actually your LoRa. Okay. Okay. For your NO3, okay, so here, the NO3 here, okay, it carries -1 charge. Okay, so the N here will actually still carries +5. So from here to here, it's like the case we say, right? It doesn't really do anything related to the oxidative states of your N. Okay, but if you look at this, there's actually another N here where it's actually oxidation number goes to +4, right? So here to here, you can see it goes from +5 to +4. Therefore, it's gaining 1 electron. Therefore, this will be your G rock. Okay. So let's write this down. Your LoRa will be Cu becoming CuNO3 2. Okay. Your G rock will be HNO3. That's becoming NO2. Okay, so this is actually things that you can write out first. Okay. Second step is actually trying to balance the atoms, right? So if you look at your target atoms, one copper here, one copper here. So your copper is actually already balanced, right? Then you need to balance the other thing, right? You have NO3 here. Okay, so NO3, to balance this, you need to actually add in the things that show up in your on your reactant side, right? So since you have two NO3, then therefore you know you need to add in two equivalent of HNO3. Okay, so they can actually balance the number of NO3s on both sides. Okay. Once you balance that, then you will realize that you add in actually two extra protons on the left-hand side. Therefore, To balance that, we need to add in 2H plus to balance the protons on both sides. Okay, so up to this point, you actually balance all the atoms for your LoRa. Okay, then we can actually move to your GROC. Okay, so once you move to your GROC, you can see the species, the atom that actually undergo the GROC is actually nitrogen, right? So that's actually your target atom. And you can see your target atom is actually already balanced. Okay, so the next thing is actually you want to actually balance your oxygens and also balance your protons. Okay, so if you look at this, you have 3 oxygen here and then 2 oxygen there, right? So on the product side, you're actually missing 1 oxygen, right? So to compensate that missing of oxygen, that you add in 1 H2O. Okay, so once you do that, then all the oxygen will be balanced. Okay, but once you add in H2O, you introduce 2H on your product side, but you only have 1H on your reactant side. Therefore, we know you need to add in 1 more H plus, so you can actually balance all the H here. Okay, so after you do that, then all your GROC is balanced as well. Okay, then we can actually move on to the step number 3, which is actually to balance the charges of your LoRa and GROC. Okay, so if you look at your LoRa, copper doesn't carry any charge, 2HNO3 doesn't carry any charge. Okay, copper NO3 too doesn't carry any charges. Okay, 2H plus carries 2 plus 2 charges, right? So to balance this one, what you need to do is actually you add in 2 electrons so that these 2 will cancel out, then left and right will be balanced. Okay. For your GROC, okay, so this doesn't carry any charge, this carries positive 1 charge. This doesn't carry any charge, this doesn't carry any charge. Okay. So to balance this one, then we know we need to add in 1 electrons to balance out the charges on both sides. Okay, so that's actually how we do for the step number 3. Okay. After that, then we check the electron was given out from your LoRa. Is it the same as the electron is uptake by your GROC? So apparently they are not the same, right? So we need to actually multiply your GROC by 2 so that we can actually add all the things together. Okay, so once you do that, we're going to get copper plus 2HNO3. That's from your LoRa, right? And then plus HNO3 plus H plus 1 electron. So that's actually what you get from your GROC. Okay. And then you're going to get CuNO32 plus 2H plus 2 electron plus NO2, okay, 2 NO2, sorry. So here should be 2HNO3, 2H plus 2 electron. Okay, 2 NO2 plus 2 H2O. Okay, so once we have all the things, then we can see that 2 electrons will cancel out. Okay, 2H plus, 2H plus will cancel out. Okay, so once you have all these things cancel out, then you can actually reorganize your equation, which you're going to have copper S plus 4HNO3. That's going to give you CuNO32 plus 2 NO2 plus 2 H2O. Since now you're actually looking for the coefficient in front of your H2O, therefore the answer will simply equals to 2. Okay, so that's actually how you solve question number 4. Okay, question number 5. Sorry, my computer is somehow become very slow now. Okay, back. Okay. Question number 5. Balance the following equation in acidic solution. Okay, acidic solution again. You use H plus for your H. You use H2O for your missing O. Okay. Using the lowest possible integer and give the coefficient of H2O. Okay, again, it's about the H2O. Okay, so let's look at this equation. It looks actually quite complicated here. Okay, again, first thing is actually trying to analyze the oxidation numbers, right? So NaCl, okay, so Na is actually 1A group, so you know it's positive 1. Cl is actually 7A, it's negative 1. Okay, H2SO4. Okay, so here, remember in the beginning I say SO4 2 minus is actually the complex anion, right? So you can actually treat it as the just a fixed species. Okay, you don't need to worry too much about its oxidation number. Okay, so for that we can just skip for now. Okay, and then look at the MnO2. It's overall neutral. Oxygen is -2. You have 2 of them. Therefore, you know your Nn will be +4. Okay. And then we'll move on to here. Okay, SO4 by itself is actually -2. You have 2 sodium, right? So this will be +2, but you have 2 of them. Therefore, your sodium is still +1. Okay. MnCO2. So here your Cl will be -1. Therefore, your Nn will be +2. Okay. And then H2O. H will be just +1. O will be just -2. Cl2, okay, is actually a monoatomic species and it's neutral, therefore the oxidation number is going to become 0. Okay, so once you actually list all the things out, then you start to actually try to identify who actually undergo the oxidation number changes. Okay, so typical Na is not the one you're going to looking for, okay? So then we check out Cl. Cl, you start from -1 on the right-hand side. On the product side, you have Cl in the -1, so this is actually not the one you are looking for, but this one is the one. Apparently, you undergo oxidation number changes, right? So you go from -1 to 0. Therefore, the oxidation number increase, right? Therefore, you undergo oxidation. So this will be actually your LoRa. Okay. Then we're actually looking for another atom that undergo the G-rock, right? So if you check out your manganese, you start from +4, and then here you end up with +2. Therefore, you're gaining 2 electrons, right? So this to here is actually your G-rock. Okay, so Once you identify your LoRa, once you identify GROC, then you just write out those species, okay? So your LoRa will be NaCl, it becoming Cl2. And then your GROC will be MnO2, and then becoming MnCl2. Okay, so those are the species that you have. Okay, then we want to actually balance each individual hap reaction first. Okay, so if you look at your LoRa, okay, the species that you're actually looking for is, okay, Cl2 is actually your center atoms, right? So balance that first. Okay, so you have 2 Cl on the right hand side, therefore you multiply 2 on your left hand side. So you can just balance that center target atom first. Okay. Once you do that, then you realize that, okay, you have 2 Na on the reactant side, but you don't have any Na on your product side, right? Therefore, you want to actually introduce the Na, right? And you look back your equations, and you will realize that the only species that can provide you Na is your Na2SO4. Okay, so that's actually a species you need to use to balance your Na. Okay, so it's Na2SO4. Okay, so once you add that Na2SO4 on your product side, then you introduce your so you balance your Na, but at the same time you also introduce the SO4 on the product side, right? So you're actually trying to balance the SO4 using the things that you have on your reactant side. Okay, so in this case, the species that can give you the SO4 is the H2SO4, right? Therefore, we add in H2SO4 here. Okay, so by now, then you balance the SO4, right? Now, once you do that, then you realize, okay, then we actually have something extra, right? You have 2 extra H on your reactant side. Therefore, you need to actually balance that. Okay, so here, since we have acidic solution, therefore, the things you do is actually you add in 2H plus to balance that 2 extra H on the reactant side. And up to this point, you balance all your atom for your LoRa half reaction. Okay. Similarly, want to actually do the same thing for your GROC, right? Your target atoms for your GROC is actually manganese, right? So manganese here, you have 1, and then 1 on the product side. So it's actually already balanced, right? Then the next thing is actually you want to actually balance the Cl2. Okay, so here I want to point out that, okay, you will always balance the missing oxygen or missing hydrogen at the very end. Okay, you need to actually balance all the other atoms that show up in your equation before you can actually do that. Okay, so to balance the Cl2, right, then you're actually looking for the species on the reactant side that contains your Cl, then the only species that contains that is actually your NaCl, right? Therefore, you want to add in 2 equivalent of NaCl so that you can actually balance your Cl. Okay, but once you do that, you introduce your Na again, right? So you want to actually find something on your product side that can provide you Na. So in this case, again, you're going to see Na2SO4 is actually the species that can actually serve this purpose. Okay, so once you add in this, again, you're going to balance your Na by you introduce the SO4, right? Therefore, you know you need to add in H2SO4 to balance out the SO4. Okay, so once you did that, then you can see that the only thing that remains that's not balanced is actually your H, right? So once you have that situation appear, then you know you can actually start to balance your H and then the oxygen. Okay, so here you can see that you have oxygen here, you have H here, right? So these are the things that you want to actually start to balance now. Okay, so to balance the things, what I will do is actually I typically just start with balancing the oxygen because adding the H on both sides is a lot easier. Okay, so with that being said, okay, since here you have two oxygens, right? So I'm going to add in two H2O. Okay, so once you see that, then you can see the oxygen will be balanced. Okay, and then here on the right hand side, you have 4H. On the left hand side, you only have two, right? Therefore, you also want to add in 2H plus on the left hand side. Okay, and by doing that, you're going to balance all the atoms for your G-rock. Okay, so this question is actually very interesting because you need to actually first try to balance all the non-oxygen, non-hydrogen species first before you can actually really using the H2O and H plus to balance your H and O. Okay, so with all the things being said, and we balance all the atoms for your LoRa and the G-rock. The next thing will be to balance the charge of your LoRa and G-rock, right? So if you look at this, is neutral, right? And that is neutral. This is neutral. This is neutral. And this is actually +2. Therefore, we know we need to add in 2 electrons, okay, to balance it solely on the both sides. There will be has no net charges, okay. Similarly, okay, so here you have 2 plus, this is neutral, less neutral, this is neutral, this is neutral, this is neutral, this is neutral. Therefore, you can see you need to add in 2 electrons on your product side so that the charges on both sides will be balanced. Okay, so after you do that, then we have balanced both the atom and charge for your LoRa and the G-rock. Okay. And then the next step is actually to check whether the electron given out from LoRa is the same as the electron got accepted by your G-rock. Okay, and then the answer is yes, right? So all you do is actually you just adding up. Okay, so to NaCl, therefore you have 4 NaCl plus MnO2 plus H2SO4, H2SO4. So I have 2 H2SO4, okay, plus 2H plus 2 electron. Okay, so those are all the species you have for your reactant, right? For the product, you have Cl2 plus MnCl2 plus 2 Na2SO4 plus 2H plus 2 electrons plus 2H2O. Okay, so the things gets very long, right? And then you start to compare both sides, right? So 2H plus on the left-hand side, 2H plus on the right-hand side, 2 electrons on the left-hand side, 2 electrons on the right-hand side. Therefore, it all cancels out, right? So the next equation will be 4 NaCl plus MnO2 plus 2H2SO4. That's going to give you Cl2 plus MnCl2 plus 2 Na2SO4 plus 2 H2O. Since we're actually looking for the coefficient in front of your H2O, therefore the answer will be simply equals to 2. All right, so let's actually how you solve this looks very complicated question number 5. Okay. Question number 6. Balance the following equation in basic solution using the lowest possible integer to give the coefficient of H2O. Okay, again, it is a basic solutions, right? Therefore, you are going to balance the missing H using H2O, balance the missing O using 2OH minus. Okay. Okay, so let's look at this equation first to figure out, okay, the oxidation number of each different species. Okay, so CrO4, so this one should be subscript. Okay, so CrO4 2 minus, okay, you have 4 oxygens. That's actually -8, right? The overall is actually negative charges. That means actually your chromium is actually +6. Okay. CuS is actually a monoatomic species in its neutral form. Therefore, the oxidation number will be 0. Okay. CrOH3. Okay, OH carries -1 charges, right? 3 of them that give you -3. Therefore, your chromium in this case will be +3, so that the overall molecule will be neutral, right? Similarly, OH2 is -2, therefore your copper will become +2. Okay, so then once you identify all the things, next thing is to identify, okay, who is actually a LoRa, who is actually a G-Rock, okay? Copper go from 0 to +2, right? So they will be your LoRa, okay? CrO4, 2 minus becomes CrOH3. Okay, so you get 3 electrons, so that's actually your G-Rock. Okay, so again, LoRa, G-Rock. Okay, so your LoRa is Cu becoming CuOH2. Okay, and then G-Rock will be CrO4 2 minus becoming CrOH3. Okay. Then we want to actually balance the atoms, right? So look at your target atoms. Okay, 1 copper on left-hand side, 1 copper on right-hand side. So copper by itself is actually balanced. Okay. Then you look at the things that's extra, right? The extra is actually the OH, right? So if you have 2 OH minus on the left-hand side, right? Therefore, all we do is actually we add in 2 OH minus on the left-hand side to balance your OH. Okay, so up to this point, it is actually already balanced, right? On the right-hand side, for your G-Rock, then focus on your target atom first. Okay, 1 chromium on the left and 1 chromium on the right. So your chromium is already balanced, right? So then we can actually look at the other atoms. Okay, so you can notice that on your right-hand side, you have 4 oxygens. Okay, and on the right-hand side, you have OH3, right? So this actually go to the very similar situation that we have in our first equations, first problems, right? So because the things that is the extras on the right-hand side is OH, right? So you first go back to your right-hand side, see how many oxygen they have. So you have 4 oxygens on the reactant side. Therefore, you expect to have totally 8 OH minus on the right-hand side, right? Because one missing oxygen, you need 2 OH minus to compensate in the basic solution, right? So since right now we have 4 oxygens on the reactant side, therefore we expect 8 OH minus on the product side. But here you already have 3 on your product side, right? Therefore, all you need to do is actually you add in 5 OH minus to balance it. Okay, so once you do that, your oxygens will be so your oxygen, so you can see you're going to have totally 8 oxygens and 8 protons on the right hand side, right? And then on the left hand side, you have 4 oxygens, right? So to account for the missing remaining proton H or the O, then you need to add in the H2O. Okay, so what you need to add in is actually 4 of them. Okay, so by doing that, you can actually balance both your oxygen and hydrogen for your G-Rock. Okay, so after you do that, then all the atoms are balanced. Okay, then we can just move on to step number 3 to discuss the charges, right? So if you look at your LoRa, this is 0, this is actually -2. So on your right-hand side, you have totally -2 charges, right? On your right-hand side, this is actually neutral, right? So in order to balance that, you need to add in 2 electrons. So that on the right-hand side is also -2 charges, okay? Then you can move on to your G-Rock. Okay, so this is actually -2. Okay, this is actually neutral. This is neutral. This is actually -5. So you can see your polar side is 3 electron more than the left-hand side, right? So you add in 3 electrons on the left-hand side. Okay. Then you balance all the charges. Okay, so after this will be you compare the electron that was given out from our LoRa, which is actually 2 electrons, right? And then compare that, is that the same as your G-Rock, but they are not, right? One give out 2, one accept 3, right? To make it the same, then we to actually multiply your LoRa by 3, multiply the G-Rock by 2, so that all the electrons will be balanced. Okay, so once you do that, then you're going to have 3 copper plus 6 OH minus plus 6. So this multiplied by 2, right? So 6 electrons plus 2 CrO4, 2 minus plus 8 H2O. So that's all the things you have for your right-hand side. On the product side, you're going to have 2 CuOH2, sorry, 3 CuOH2 plus 6 electrons plus 2 CrOH3 plus 10 OH minus. Okay, so once you have that, then you can see 6 electrons cancel out with 6 electrons. Okay, 6 OH minus will make this one become simply 4. Okay, so the next equation you are going to have is 3 Cu plus 2 CrO4, 2 minus plus 8 H2O. They give you 3 CuOH2 plus 2 CrOH3 plus 4 OH minus. Okay. So things right now, the things you are interested in is the coefficient in front of your H2O. Therefore, the coefficient you want to answer will be simply equals to 8. Okay, so that is actually how you solve question number 6. Okay. Question number 7. Identify the oxidizing agent and the reducing agent in this reaction. Okay, so again, first of all, it's actually to analyze the oxidation numbers, right? So if you look at this, okay, NO3 minus, right? So it's actually -2 multiplied by 3, so it's -6, right? The overall charge is -5. That means actually your N is simply +5. Zinc is actually a monoatomic molecules at the neutral state, therefore the oxidation number will be 0, right? O is -2, H is +1, nothing special, right? It's the same, right? +1, -2. Okay. Zinc, OH, 4, 2 minus, okay. One single OH is actually -1, right? You have 4 of land, that's actually -4. But the overall charge is actually -2, therefore it tells you the zinc is +2. Okay. Very last one, NH3. Okay, you have 3, H is +1. You have 3 of land, so it's +3, right? But the overall is actually neutral. That means actually N is -3. Okay, so once you do this, then you can realize that the oxidation number of your nitrogen going from +5 to -3, right? So this is actually your G rock, right? And then for your zinc, you go from 0 to +2. That's actually your LoRa. Okay, so you know your LoRa is your zinc. Okay, and then okay, zinc to zinc OH 4 2 minus, right? Your G rock will be your NO3 minus becoming NH3. Okay, so then we want to know who is actually the oxidation agent, who is actually the reducing agents, right? So what LoRa stands for is actually the species is actually losing electron. Okay, it's undergo an oxidation reaction, right? And the R is actually it serves as a reductant, right? Okay, so the other name of reductant is actually your reducing agent. Okay, therefore we know zinc, okay, will be actually your reducing agent. Okay. Similarly for the G rock, right? G rock is actually gain electrons. Okay. By itself is actually reduced. It can actually serve as a oxidant, right? Okay, so oxidant is basically your oxidizing agent. Okay, so with that being said, like we know the NO3 minus is actually your oxidation agent. Okay, so we actually we spent actually most of time in today's lecture to discuss how you can actually balance a redox reaction. Okay, so the most important thing is actually, can you identify the oxidation numbers of all the atoms inside your equations, right? And then you need to really get familiar with the 4 steps, how you can actually balance the redox reaction, right? The first step is actually to identify 2 half reactions, meaning you need to be really good at to identify who is actually your LoRa, who is your G-Rock. Okay, and after that, balance your LoRa and G-Rock. Okay, balance the central atom first, and then balance all the other atoms that doesn't belong to O or H, right? And then the very last one is actually balance your O and H based on the solution that you have. If you have acidic solution, okay, if you have acidic solution, then you use H plus to balance your H plus for your H, right? You use H2O to balance out your O, okay? But if you balance your basic solution, then using the H2O to balance your H, and then using the OH minus to balance your O. Okay. Typically, you will always balance the O first before you balance your H. Okay, so it's actually something I think it's actually very useful tips for you to know. Okay, and then once you balance all your atoms, the next thing is actually balance the charge. Okay, using electrons for your LoRa and GROC. Okay, the very last step is actually make sure your LoRa and GROC is giving out the same electron that your GROC want to actually accept. Once that is the case, you simply add up those two half reactions. Then you can have your balanced redox reactions. Okay, so I think that's all for today's lectures and hope you enjoyed it. Okay, I will see you next time. Bye now.